My name's Chris. Let's do science. Chris does science. Today, we're looking at the most misunderstood aspect of special relativity, that being time dilation. We have planet A and planet B separated by 7.5 light years, and we have our craft moving from planet A to planet B at 0.8 times the speed of light. Questions such as this generally ask for two things. What does the observer on planet A see? And what does the observer on the spacecraft see? So let's think about the time taken for the journey according to an observer on planet A. So you see the fact that it's relativistic speeds, and straight away you're like, I got to apply some special relativity to this scenario. Unless you have a good understanding of what that square root 1 minus v squared on c squared thing actually means. And this, my friends, and those who aren't my friends that hopefully want to be my friends, is called the gamma factor, or the Lorentz factor. So what does this bad boy actually do? So this bad boy literally transforms an observation made in one reference frame to an equivalent observation in another reference frame, which is moving at a relative velocity to the first reference frame. And I use this transformation when I don't have all of the information I need in the given reference frame to complete a necessary calculation. So what about this scenario? I want to find the time taken for that spaceship to go from A to B according to an observer on planet A. Now I already have the distance as measured by an observer on planet A alongside the speed of the object as measured by an observer on planet A. In order to find the time as measured by an observer on planet A, I don't need to make any transformation. Now why is that? Because I already have the measurements that I require from my given frame to figure out the value of the other measurement in my given frame. So it's literally your boy from year 9, the STD triangle. And there's a little trick when you've got distance in light years and speed in terms of the speed of light. And I want to show that to you right now. So unlike me and biologists, these two things actually have something in common, and that is light. So what can we do? We legit just cross out the light. So we get an answer of about 9.4 years. So that is saying, according to observer A, it takes 9.4 years for the spaceship to go from planet A to planet B. So what does the observer on the spacecraft actually see? Let's write out our time dilation equation and try and figure out what's what. So remember, our denominator is always between 0 and 1, which means t must be greater than or equal to t0. And with the knowledge that less time passes in a moving frame, it's fair to say the moving frame is t0. So let's solve for the time according to the observer in the spacecraft. Firstly, let's do some algebra and make t0 the subject. And then it's literally plug in numbers. So the time taken according to the observer on the spaceship is 5.6 years. Now I want to show you another way of coming up with this exact number by using length contraction. So let's go back to the OG question. For those of you who do not like this whole time dilation thing, there is another way of solving the problem without even using time dilation. Essentially, the question wants you to find the time taken according to this guy, the observer in the spacecraft. So what if I just use my STD triangle again? I mean, it should work, right? Of course it should work, as long as you have the measurements you need in the frame that you're using to take the measurements. So if I want to find the time taken according to the observer on the spacecraft, I need the distance according to the observer on the spacecraft and the speed according to the observer on the spacecraft. Good thing about all this special rel stuff is observer A and the observer on the spacecraft agree the spacecraft is moving at 0.8 c. So we already know this. However, the distance of 7.5 years is the distance according to the observer on planet A. Now here's the secret. If only there was a way for us to change the distance observed by observer A to the distance observed by the observer on the spacecraft. Of course there is. And that's the length contraction formula. So whilst the observer on planet A sees 7.5 light years, the person on a spacecraft is moving through space. So the person on a spacecraft sees that 7.5 light years contract. This is the distance that the observer on the spacecraft sees. So we'll now throw this up here. Lo and behold, chuck that in your calculator, 5.625 years. Easy peasy.